Today, in this video lecture, we will see numerical based on Euler's formula. So, first, read this numerical. The steel rod 5 meter long and of 40 diameter is used as a column with one end fixed and other end free. Determine the crippling load by Euler's formula. Crippling load, that means in another word it is buckling load. So we will have to find buckling load or crippling load, and they given us that steel rod, see, steel circular rod, and length of that steel rod is 5 meter, and dia is 40 one end fixed, that means here it is fixed, then other end is free. So first write given data. Let us consider capital D as dia of this steel rod. See this E, Young's modulus or modulus of elasticity of steel. This is given 200 GPa, that means 200 into 10 raised to 3 MPa. MPa, that means Newton per mm square. And original length of the actual length of that steel rod is 5 meter. That means 5 into 10 raised to 3 mm, 5000 mm. And our objective, our aim is to find that crippling load. So what is crippling load? See, crippling load we denote by this PC. Okay. So first, see solving methodology. Our PC crippling load for one end fixed and other end free in conditions formula is pi square EI upon LE square. What is this LE? LE is effective length. Pi square is constant. E is modulus of elasticity. This is given quantity. See in numerical, this is given quantity. And I, what is I? I is moment of inertia. And so this moment of inertia for circular shape, we all know that we have seen this in our previous, like, second chapter, that xx yy for both ixx and iyy, moment of inertia of that circle is same, that means pi d raised to 4 by 64. So this I is also known quantity now. And LE, see what is this LE? LE for one end fixed and other end free. So effective length, that means it is twice L, and L we all know that actual length 5000. So that means this LE is 10,000, and unit is mm. So like that way we will solve this numerical, like put this LE IE on that equation, and like we will get this PC, crippling load or buckling load. So first find that effective length LE. Solution. So effective length L for that column is 2L. That means 2 into L is 5000. So effective length is 10,000 mm. Okay. Next, our objective is to find that moment of inertia. And see, always use least moment of inertia because of safer design. So least moment of inertia, as we all know that moment of inertia for circular shape is similar. So pi d raised to 4 by 64 pi d is 40 mm. So 40 raised to 4 by 64. So pi into 40 raised to 4 divided by 64, it is 125 point, no, it is 125663.70. And moment of inertia unit is mm raised to 4. So next, L E. So just use this crippling load equation, pi square E I upon L E square. Pi square is a constant, E is 200 into 10 raised to 3 Newton per mm square, and I is 125663.70, and divided by L is 10,000 mm. So first understand that, see, unit of this is Newton per mm square. This is E, Young's modulus or modulus of elasticity. This is mm raised to 4, and this is mm square. So this mm square cancel, so remaining is mm square, and this mm square also cancel, so remaining is only Newton. So that crippling load or buckling load that will come in Newton. So pi square into 200 into 10 raised to 3 into 125663.70 divided by 10,000 square. So it is 2480.50 Newton. So this is buckling load. So at this load, this column will buckle. Yes. And in kilonewton, it is 2.48 kilonewton. So just see, for solving this numerical, we need like these formulas. We need to remember these formulas, this moment of inertia, this crippling load, this effective length, and with the help of these formulas, like we are able to solve this numerical. So thank you very much.